Computational Dynamics of Spaceships in Design and Structures. Part 1. Robotic Voice Narrator, Paul. Second narration, Carl Sagan, Education from the Cosmos Episodes. Third narration, NASA, When Neutron Stars Collide. No matter what the spaceship structure form design would be, there are several initial technical design terms that you should consider in your first conceptual drawings for implementation. 1. Spaceship mass compositions at rest frame. 2. Relativistic isolation of the center of momentum. 3. Navigation field dynamics. 4. Systems management operability assurance. For compound objects made of many smaller objects, some of which may be moving, and sets of unbound objects, some of which may also be moving, only the center of mass of the system is required to be at rest, for the object's relativistic mass to be equal to its rest mass. The system on average must be at rest to be weighed. It must have zero net momentum, which is to say, the measurement is in its center of momentum frame. For example, if an electron in a cyclotron is moving in circles with a relativistic velocity, the weight of the cyclotron plus electron system is increased by the relativistic mass of the electron, not by the electron's rest mass. Again, in special relativity, the rest mass of a system is not required to be equal to the sum of the rest masses of the parts, a situation which would be analogous to gross mass conservation in chemistry. For example, a massive particle can decay into photons, which individually have no mass, but which as a system preserve the invariant mass of the particle which produced them. This is because the total energy of all particles and fields in the system must be summed, and this quantity, as seen in the center of momentum frame, and divided by C2, is the system's invariant mass. If we would like to preserve a structural dimension, we have to consider to define an idealized but drawable boundary around this system's structure, where no mass energy is allowed to cross it. In technical term, this is an isolated system. To understand the technical term of the relativistic mass, we calculated the invariant mass of a system, that is the total energy of the system divided by C2. C squared in the center of momentum frame, where the center of momentum is zero. Conservation of invariant mass also requires the system to be enclosed so that no heat and radiation and thus invariant mass can escape. A physically enclosed or bound system does not need to be completely isolated from external forces for its mass to remain constant, because for bound systems these merely act to change the inertial frame of the system or the observer. Though such actions may change the total energy or momentum of the bound system, these two changes cancel, so that there is no change in the system's invariant mass. This is just the same result as with single particles. Their calculated rest mass also remains constant no matter how fast they move, or how fast an observer sees them move. The rest mass of a composite system is not the sum of the rest masses of the parts, unless all the parts are at rest. The total mass of a composite system includes the kinetic energy and field energy in the system. In special relativity, mass is not converted to energy, for all types of energy still retain their associated mass. Neither energy nor invariant mass can be destroyed in special relativity, and each is separately conserved over time in closed systems. Thus, a system's invariant mass may change only because invariant mass is allowed to escape, perhaps as light or heat. Thus, when reactions, whether chemical or nuclear, release energy in the form of heat and light, if the heat and light is not allowed to escape, the system is closed and isolated, the energy will continue to contribute to the system rest mass, and the system mass will not change. Only if the energy is released to the environment will the mass be lost. This is because the associated mass has been allowed out of the system, where it contributes to the mass of the surroundings. To the stage, you have to consider to present a clear and solid design implementation pathway, supporting your design strategy no matter the complexities you have to deal. Beyond the constrained conditions that may arise from the physical properties from materials configuration performance, it is equally important to integrate with these factors deformation protection, based on energy mass correlation, to guarantee operation limits and set maintenance and service research and development protocols, if they are not exist. Maintenance prognostics. Orient your systems engineering integration gears. to link in a solid way all the information that is required from the distributed control components to operate in proper time, so to make prognosis, initially at rest frames measurements without relativistic operators. Relativistic operability. Analyze and simulate operations parts per function that are contributing independently to the overall relativistic profile of the spaceship. This will help you to designate critical reconfiguration and adjustments as extended operation functions during space travel near sea velocities. All these will also minimize the human risk factor, that is the overall goal. Shapeforms and structures conditions. The name mass belonging to the magnitude of a 4-vector to a very different concept, the time component of a 4-vector. It makes increase of energy of an object with velocity or momentum appear to be connected with some change in internal structure of the object. In reality, the increase of energy with velocity originates not in the object but in the geometric properties of spacetime itself. While spacetime has the unbounded geometry of Minkowski space, the velocity space is bounded by c and has the geometry of hyperbolic geometry, where relativistic mass plays an analogous role to that of Newtonian mass in the barycentric coordinates of Euclidean geometry. The connection of velocity to hyperbolic geometry enables the 3-velocity-dependent relativistic mass to be related to the 4-velocity Minkowski formalism. Conditions of space travel, distinct areas and processes. The vantage points during space travel. The Doppler effect during space travel, introductory approach. Time dilation, a law of nature. A thought experiment.
Long ago, before we had figured out that the stars are distant suns, they seemed to us to make pictures in the sky. Just follow the dots. The constellation called the Big Dipper today in North America has had many other incarnations. Every culture, ancient and modern, has placed its totems and concerns among the stars, from a Chinese bureaucrat to a German wagon. But very ancient cultures would have seen different constellations, because the stars move with respect to one another. We can give a computer the present three-dimensional positions and motions of the nearby stars, and then run the patterns back into time. Every constellation is a single frame in a cosmic movie, but because our lives are so short, because the star patterns change so slowly, we tend not to notice it's a movie. 1,000,000 years ago, there was no Big Dipper. Our ancestors, looking up and wondering about the stars, saw some other pattern in the northern skies. We can also run a constellation, Leo the Lion say, forward in time and see what the patterns in the stars will be in the future. 1,000,000 years from now, Leo might be renamed the constellation of the radio telescope, although I suspect that radio telescopes then will be as obsolete as stone spears are now. Or here's the constellation of Cetus, the whale. A 1,000,000 years ago, it may have been called something else, perhaps the spear. Now let's run fast forward through 1,000,000,000 nights. Millions of years from now, some other, very different image will be featured in this cosmic movie. In Orion, the hunter, things are changing not only because the stars are moving, but also because the stars are evolving. Many of Orion's stars are hot, young, and short-lived. They're born, live, and die within a span of only a few million years. If we run Orion forward in time, we see the births and explosive deaths of dozens of stars flashing on and winking off like fireflies in the night. If we wait long enough, we see the constellations change. But if we go far enough, we also see the star patterns alter. The two-dimensional constellations are only the appearance of stars strewn through 3 dimensions. Some are dim and near, others are bright but farther away. Could a space traveler actually see the patterns of the constellations change? For that, you must travel roughly as far as the constellation is from us. Here, we're traveling hundreds of light years, circling all the way around the stars of the Big Dipper. The inhabitants of planets around other stars will see very different constellations than we do, because their vantage points are different. Paolo says goodbye to his little brother Vincenzo.
Ciao, Vincenzo.
Ciao, Mom.
And rides off. He's now going more than half the speed of light. He's almost catching up with his own light waves. This compresses the light waves in front of him, and his image becomes blue. The shorter wavelength is what makes blue light waves blue. Also, Paolo becomes skinny in the direction of motion. This isn't just some optical illusion. It really happens when you travel near the speed of light. As he roars away, he leaves his own light waves stretched out behind him. Long light waves are red. We say that his receding image is red-shifted. Now, Paolo leaves for a short tour of the countryside. He experiences something even stranger. Everything he can see is squeezed into a moving window just ahead of him. Blue-shifted at the center, red-shifted at the edges. To a passerby, Paolo appears blue-shifted when approaching, red-shifted when receding. But to him, the entire world is both coming and going at nearly the speed of light. Roadside houses and trees that he's already gone past still appear to him at the edge of his forward field of view, but distorted and red-shifted. When he slows down, everything again looks normal. Only very close to the speed of light does the visible world get squeezed into a kind of tunnel. You would really see these distortions if you could travel near the speed of light. Someday, perhaps, interstellar navigators will take their bearings on stars behind them, whose images have all crowded together on the forward view screen. The most bizarre aspect of traveling near the speed of light is that time slows down. All clocks, mechanical and biological, tick more slowly near the speed of light. But stationary clocks tick at their usual rate. If we travel close to light speed, we age more slowly than those we left behind. Paolo's watch and his internal sense of time show that he's been gone from his friends for only a few minutes. But from their point of view, he has been away for many decades. His friends have grown up, moved on, and died. And his younger brother has been patiently waiting for him all this time. The two brothers experience the paradox of time dilation. They've encountered Einstein's special relativity.
Vincenzo.
This was just a thought experiment, but atomic particles traveling near the speed of light do decay more slowly than stationary particles. As strange and counterintuitive as it seems, time dilation is a law of nature.
Conditions of space travel, distinct areas and processes. There is a speculative notion that if there were a black hole with the same mass and charge as an electron, it would share many of the properties of the electron, including the magnetic moment and Compton wavelength. This idea is substantiated within a series of papers published by Albert Einstein between 1927 and 1949. In them, he showed that if elementary particles were treated as singularities in spacetime, it was unnecessary to postulate geodesic motion as part of general relativity. Practically, though particle experiments cannot probe arbitrarily large energy scales, and so quantum electrodynamics-based experiments bound the electron radius to a value smaller than the Compton wavelength of a large mass, on the order of 10 to the 6 power of giga-electron-volt. With appropriate tensor fields representing physical quantities, such as matter and momentum densities, we have a piece of a possibly larger spacetime. The simplest way to define this tensor is to define it in compatible local coordinate charts, and verify that the same tensor is defined on the overlaps of the domains of the charts. The Schwarzschild chart is a kind of polar spherical coordinate chart on a static and spherically symmetric spacetime, which is adapted to these nested round spheres. Conditions of space travel, distinct areas and processes. As a thought experiment for spaceship design purposes, including stochastic scaling for physical properties of space-time, the reverse engineering mechanisms of a colliding neutron-star merger is one of the most profound justification of the boundaries of energy-mass relation for spaceships, conditions and distinct areas for processes for computational dynamics and for space travel.
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma-ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma-ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's SWIFT satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes. Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging star's magnetic field organizes itself into outwardly directed components capable of forming a jet. The Damiana supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows two neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic strength 1 billion times greater than the Sun's. The simulation shows the same disorderly behavior of the matter and magnetic fields. Both structures gradually become more organized, but what's important here is the white magnetic field. Amidst this incredible turmoil, the white field has taken on the character of a jet, although no matter is flowing through it when the simulation ends. Showing that chaotic magnetic fields suddenly become organized as jets provides scientists with the missing link. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.
Your basics in brief. The total energy of all particles and fields in the system must be summed, and this quantity, as seen in the center of momentum frame, and divided by C2, is the system's invariant mass. Conservation of invariant mass also requires the system to be enclosed so that no heat and radiation and thus invariant mass can escape. The total mass of a composite system includes the kinetic energy and field energy in the system. Only if the energy is released to the environment will the mass be lost. This is because the associated mass has been allowed out of the system, where it contributes to the mass of the surroundings. The connection of velocity to hyperbolic geometry enables the three-velocity-dependent relativistic mass to be related to the four-velocity Minkowski formalism. If elementary particles were treated as singularities in space-time, it was unnecessary to postulate geodesic motion as part of general relativity. Practically, though particle experiments cannot probe arbitrarily large energy scales, and so QED-based experiments bound the electron radius to a value smaller than the Compton wavelength of a large mass,